Hello everyone and welcome to Fisimania. In today's video, we're going to do the second class for cosmology. Today we're going to be learning a lot more about cosmology, so please stay tuned. And without further ado, let's go. All right, so what we're going to be doing for today, so the content for today are going to be three simple things, but which are going to require some time. So the first thing is going to be looking at the geometry of space. Then we're going to take a look at the FLRW metric. This is a metric which basically describes the geometry of a homogeneous and isotropic universe. So basically it's also looking at some type of geometry, and it's going to be the geometry of our universe. And then we're also going to take a look as well at some distances in cosmology. Okay. Although these are not going to be the only distances that we will look at in cosmology, these are some of the initial distances that we're going to take a look at. So distances in cosmology. Okay, so let us get started with the geometry of space. And so for space, what we have is basically we have two types of geometry. The first one is going to be what we call Euclidean geometry, and then the second one is going to be the non-Euclidean geometry. So the Euclidean geometry is going to be what represents a flat space, or basically is going to be the same thing. For example, as let's say, imagine we have a piece of paper, and so this paper is flat. So this will be a Euclidean geometry. Again, it doesn't have to be a two-dimensional being or a two-dimensional object or a space. It can be also a three-dimensional space. So let us start with the Euclidean one. Euclidean. Okay, and remember this represents a flat space. Okay, the Euclidean geometry is a flat space. And so basically any geometry can be represented with its metric, as we saw in the past video, because basically it describes how, for example, two points are separated, and if whether they have curve, whether it's expanding. In this case, just looking at the geometry, okay, the metric can be written as ds squared equals to dx squared. Also, this is two-dimensional, okay, so we're going to start with a two-dimensional space. It's going to be dx squared plus dy squared. And so again, this is a representation which is called Cartesian representation. And as you can see, the geometry, the symmetries that this kind of a space will have is basically kind of like linear geometry. So this is basically the same as, for example, having a coordinate system which is just linear, right? And then, for example, it's going to be the same whether you are in this point or whether you translate yourself to these points. The physics, the geometry here is going to be the same. Then we have also different representations. For example, another representation can be more of a circular representation, and this is what it's called the polar coordinates. So in this case, we're going to represent our metric in polar coordinates as dr squared plus r squared times d theta squared. And again, this is a circular kind of like approach to the geometry, okay, but in a flat space. And so what this will represent in this case is, imagine that we have our coordinate system, okay, and then the geometry or the symmetries are circular. So in this case, what we're going to have is, for example, some type of circle where we have some specific radius, okay, as you can see here, as is given by this little r. And so this radius is going to be the point at which we are evaluating our geometry. And then the theta here is going to represent whatever change we are representing in our geometry. Easily, this can be generalized to a three-dimensional space. And so in a three-dimensional space, this metric is going to be given by dx squared plus dy squared plus dc squared. Again, in the Cartesian representation, so basically in that linear geometry. But then how do we represent it in a three-dimensional space, which has kind of like a spheroid in this case, right? The three-dimensional part of a circle is going to be a sphere. So this is actually going to be given by dr squared plus r squared d theta squared, and then which is the next coordinate, which is going to be represented by our sphere, is going to be the phi angle, which is our third coordinate. So r squared sine theta squared times d phi squared. And so as you can see, we have some common factors. So we can write this one as dr squared plus r squared times d theta squared plus sine squared theta times d phi squared. And actually, this term right here is what is known and what is defined as the solid angle. So the r squared plus r squared times the solid angle, okay? And so this d lambda is what we're going to call. Now let us take a look at non-Euclidean geometry. So again, this is for a non-flat space, non-Euclidean, Euclidean geometry. Again, non-flat space. And what we can see is then in a non-Euclidean geometry, we can have actually two types of non-flat spaces. The first one is going to be a hyperbolic space, which what this means, okay, hyperbolic. So let us just go right ahead and look at it. Hyperbolic space. In this type of space, what we can say is basically we have two lines that in a region that is locally to us, these two lines are going to be parallel to each other, okay? And so once you go out of this region, so basically once you go out your local region of space, then as you go out, what you're going to see is that these lines are going to start separating from each other, and they're basically going to be curving away from each other. So what we will see if we were trying to represent it in a two-dimensional space is that we have locally two lines, okay? So these red dotted lines are going to represent kind of like our local space. These two lines here are parallel to each other, but then once we go out of that region, then what we see is basically our lines start to curve away given the geometry of this hyperbolic space. And what we can say basically at this point is that the curvature of this specific space is going to be a negative curvature, okay? So it has some curvature because it's non-flat, negative curvature. And we represent that curvature with k, with this constant k equals to -1. So basically what we say is a negative curvature. Now in two dimensions, then the metric is going to be given by ds squared equals to dr squared plus this capital letter R squared times the hyperbolic sine squared times R over capital letter R times d theta squared, okay? What is this? What will this R, big R represent? This capital letter R represents basically kind of like the radius of the universe. So basically, if we are in a space, which is our universe, and we have a hyperbolic space, then this R represents the radius of that whole of this whole space. And then this capital letter R will represent simply the radius at which we are evaluating our geometry in this space. Now we can also now do the same thing in three-dimensional space, which will give us basically the same thing, but this time, instead of just multiplying by the theta square as we have here, then we will be actually multiplying by the solid angle square, okay? So what we saw before as being this specific parenthesis right here. All right, so what is the second space that we can have in a curvature in a non-Euclidean geometry? In a non-Euclidean geometry, the second space that we can have is an elliptic space. Elliptic space. And so in this space, we basically have the opposite of what we have in a hyperbolic space, where if we have two lines that are parallel to each other, as we go out of that local region, then what we see is that the two lines curve towards each other. And then we say basically that we have a positive curvature in this case. So basically our picture will be drawn like this, where we have two lines and then they kind of like curve towards each other, okay? As we go out of that local region. And then we say again, we have positive curvature. I write very bad, but with k equals to +1 in this case, okay? And then right now you don't see where these positive k's or negative k's come in, but you'll see it in a little bit when we go to the FLRW metric. So now for this elliptic case, then the two-dimensional metric is given by ds squared equals to dr squared plus capital letter R squared times sine squared of R over R times d theta squared. And then in 3 dimensions is going to be exactly the same thing, but again, once again, we're just going to multiply by the solid angle instead of the theta alone, okay? So again, very simple, very easy. And this is kind of like all the possible geometries that we can have, or I mean, some of the possible geometries that we can have, depending on which type of geometry you have in your space. But now we're going to take a look at what we actually have when we have a universe which is homogeneous and isotropic as the cosmological principle dictates. In this case, this is what is known as the Friedman-Lemaitre Robertson Walker metric, or FLRW metric, okay? So this metric again is for a universe which is homogeneous and isotropic, and this metric now is given by the following equation, where I need to remember you that we are in a 4-dimensional space, since we have 3 dimensions of space and then 1 of time. So basically we are in a space-time of 4 dimensions. And so the first component that we're going to see is going to be the change in time, okay, which has this negative in front, plus a square of t, so basically the scalar factor square times dr square divided by 1 minus k times r squared plus r squared times the solid angle square, okay? And so basically now, well, this is what is given for the metric in a homogeneous and isotropic universe. So let me just box this so that we know this is an important quantity. But what we're going to do now is we're actually going to derive this equation. So basically this metric. Specifically, we're going to derive the spatial part of this metric, right? Since this is the time component, but this is the spatial part. Although, I mean, obviously, so remember, this is also all of it is written in terms of natural units. So basically, this will have a c squared in front of it in order to make sure that we have the right units everywhere. But I'm talking about this being the time component since it has the dt squared. And this one is more specific about the dr squared. Anyways, let us derive this, okay? And so derivation to understand where this is coming from and what is its derivation, what we're going to do is we're going to consider a three-dimensional sphere. So basically a three sphere, which is embedded, which is inside of a four-dimensional space, okay? And you might think this is odd. Why are we doing this? But we're just trying to describe what is the geometry of a universe. Since we said we are in a four-dimensional space, actually in a four-dimensional space-time. And this will be very similar to, for example, having a piece of paper which is a two-dimensional object, which is embedded inside of a three-dimensional space, right? So that's all that we're going to imagine for now. And then we're going to say that basically the spatial component of this three sphere is given by some coordinates, which can be described by some radius, some angle, and two set of angles. And then the fourth dimension is what we're going to call the z-axis, okay? Is fourth dimension. Is going to be our c. So now, if we are in a positive curve space, right? For a positive curve space, then our metric, if we try to write it first in terms of kind of like some Cartesian components, then what we'll have is dx squared. So basically this set of coordinates for the sphere plus dc squared. And what is the relationship between c and x? In our positive curve space, this is going to be given by c squared plus the x squared, and then this is going to be equal to c squared, which this c squared is going to be some radius for our space, okay? Now, for a negative curve space, for negative, actually, let me write as negative curve space, just like this, negative curve space, then the metric is going to be given by ds squared equals to dx squared minus dc squared. And the relationship is going to be given by c squared minus x squared equals to c squared, okay, where c again is the radius. And what we're going to do now, the following thing that we're going to do is we're going to say that we're going to rescale our coordinates. And so basically now x is going to be equals to some factor a, which again is obviously going to be the scalar factor, but we're not taking into account time right now. So this is going to be something that is going to rescale our coordinates. So it's going to be a times some other x coordinate prime. And then same thing with c is going to be a times some c prime. Now, this then allows us to see that basically either for positive or negative curve space, then our metric can take the following form, where we have a squared times dx prime plus minus dc prime, and both terms are going to be squared. Then we'll have that our relationship is going to be c prime squared plus minus x squared, x prime squared equals to c squared or a squared. And now the following thing that we're going to do is actually remember that this c is just like a radius, and so this radius might be able to just we are able to just write it, for example, as some other radius which we're going to set equal to 1. So for example, let's say we call it some r, and then it can be multiplied also by this scalar factor, and this will give us basically that we have r squared times a squared divided by a squared, and then we can simply we can renormalize our space to just to that, so that that radius is basically equal to 1, and the whole thing then we can just set it up to be equal to 1. Okay, so very simple, nothing complicated, just simply setting up the right hand side equals to 1 to make our calculations that come now a little bit easier. So what we're going to do next is we're going to now substitute this dc in terms of dx squared, given this equation, obviously. So if we take the derivative, okay, or we take that change of rate in this equation in both sides, then what we end up finding is we have on the left hand side, we're going to have 2c prime times dc prime. And then this is going to be equal to plus or minus 2x prime dotted with dx prime. And this is a dotted since this is the product of two vectors. And on the right hand side, we have a constant. So the change in a constant is always going to be 0. And this is equal to 0. The 2's are going to cancel out. And then basically what we find is that dc prime is going to be given by x prime dotted with dx prime divided by c prime. And from this equation, then we can rewrite c prime as, so let me just write first the numerator here. And then the c prime, we can just rewrite it as 1 minus plus x prime squared and the square root of this term, of this expression, okay? So now we can plug that into our metric, and what we are going to find is this is a squared times dx prime squared plus or minus x prime dx prime everything squared divided by 1 minus plus x prime squared, okay? And what we can do now is realize that we can now rewrite all the possible curvatures that we can have in terms of our k or k constant that we showed before, and make sure that then we absorb these plus or minuses into that constant. So basically what we're going to do is let's define a new constant k, which is going to be equal to the same things depending on which type of k we want. So it's going to be 1, which is going to be for an elliptical space, so a positive curvature, -1 for a negative curvature or hyperbolic space. But then we also want to include the possibility that our space can be flat, right? And so what happens when we have a flat space is that we have basically our curvature is going to be 0, so that k has to be defined as 0. So this is flat space. And again, we're going to introduce it into this term here, and then by making sure that we absorb it we are absorbing these plus or minuses that we have here. So our metric now then can be rewritten as ds squared equals to a squared times dx prime squared, and then plus k times x prime dx prime everything squared divided by 1 minus k times x prime squared. You see? When again, this k is just given above. Now what we have to further evaluate is this dot product. So as you can see, we are arriving to that form that we have before, but as you can see, for example, in the denominator we don't have any case. They are sorry, in the numerator we don't have any case. They are in the denominator. So what we're going to do is now evaluate that. We're going to try to evaluate this term, this dot product, and then this term as well, so that we can relate it to um, to the r to the r to a specific radius in which we're going to be evaluating our cosmology. And so, because the universe is isotropic, what we actually have is that the dot product of this x times dx is not going to care about the angles, it's only going to care about the radial component. And then the dx squared or the dx prime can be just written as dr squared plus r squared times the solid angle, sorry, the angle squared. And then also we have to remember that x prime dotted with itself, which is x squared, is just going to care about also only the radius. And what we end up finding is then that the metric can now be written as a squared times dr squared plus r squared times the solid angle squared plus k times r squared dr squared divided by 1 minus k. Joder. Apologies, I had an interruption here, but as we were saying then, what we have here in the denominator is 1 minus k times x prime squared, or sorry, in this case, r squared, since we are already substituting. And now we only have to evaluate this term and this one. And what it ends up giving us, okay, obviously, and I'll let you do this, but you'll see, is that then we have r squared times the solid angle squared plus dr squared divided by 1 minus k times r squared, which basically proves or finishes our derivation for the metric in an isotropic and homogeneous universe. So let us finally go to the final section of this video, where we're going to take a look at some of the distances in cosmology. Again, we'll see some more distances in cosmology, but let us start with just these ones. These are some simple distances, and it's going to be a great start for us. And again, distances are a very useful thing in cosmology, so they are very important. Now, the first distance that we're going to take a look is the proper distance. And this distance is defined basically as the length of the geodesic between us and some other galaxies we are observing at a specific time. So basically at a fixed time. And again, what this means is basically we are here and then we have another object or a galaxy or a star here that we're observing, then the proper distance will be the shortest distance between us and that star, okay? So basically that's what a geodesic means. Also, for people that don't know, a geodesic is going to be basically the shortest distance in any space, or whether it's hyperbolic, elliptic, or flat, it doesn't matter. A geodesic is going to be the shortest path between these 2 points. Okay, because remember that in spaces that are not flat, so like for example, if we have a sphere, the shortest path between 2 points is not going to be just a straight line. It's actually going to be a curved path. It's going to be a curved path in that sphere. obviously that curved path can be translated into a straight line if you pass it, if you do a transformation from that space into a flat space. But again, this is what we call the geodesic in this case. Okay, so again, let me not dilate um, this topic anymore, but what I'm going to I'll give you straight what this proper distance is. So basically, because it's going to be the geodesic between us and some other point, then the proper distance is basically defined as the integral of the metric. Okay, so again, it's going to be kind of like a sum of paths due to that metric. And this is given by, so assuming, now we're going to assume a couple of things, right? The first thing that we assume is going to be basically that geodesic doesn't have any dependencies on the angles. So basically it's just kind of like a radial dependence. And then the next thing, which we're not assuming is encoded into the definition of this proper distance, is that we are looking in a specific time. So we're not looking through different times, okay? So that makes the solid angle equals to 0, but then it also makes the change in time in that metric equal to 0. So this means that the integral for this metric, which is going to give us the proper distance, is going to be given by the scalar factor at a specific time, at that specific time we are evaluating, times the integral of dr prime, or we're going to call it dr prime, divided by the square root of 1 minus k times r squared prime. And then this is going to be evaluated from the origin of our coordinate system, which is us, all the way to that specific coordinate, or all the way to that galaxy, which is at a distance r, okay? And sometimes this integral here is actually also defined as chi, and so we're going to put it here as also as chi, okay? Because you might see it in the future. And I want you to take a look that from this expression that we have here for the proper distance, we can actually also rederive the general version of the Hubble law. And what we can do to see that is basically we're going to take the derivative of the change in rate in time for both sides. And what we end up finding is that we take the dp, so basically the dp as a function of time, and then the change in time for the scalar factor, since the chi is not going to have any dependence on time. And then I'm actually going to express this even for future videos as dp dot, okay, which is going to represent that change or that derivative with respect to time. And so this is going to be dp dot equals to a dot times chi. And now we're going to do the same trick that we did in the previous videos, which was multiplying and dividing by the scalar factor. And what we end up finding is a dot a divided by a times chi. And so if you realize a times chi is just simply, again, the proper distance, right? And then a dot over a is what we defined previously as the Hubble parameter. So now what we end up finding again is basically Hubble parameter as a function of t times proper distance. So what do we have again? Is we have some physical velocity being equal to the Hubble parameter times some times the proper distance, which in this case is going to represent the physical distance that we see from us to a specific object. All right, so now let us take a look at the Hubble distance. Hubble distance. And this Hubble distance is basically defined as the distance at which we see an object to have a velocity which is equal to the speed of light. Okay, so let me just repeat again. This is the distance that we define by seeing an object which has the speed of light. Okay, so this means that if we are observing with our telescopes and then we measure the velocity of a galaxy, for example, and we see that galaxy has a speed which is equal or seems to have a speed which is going away from us with the speed of light, then that distance is what we define as the Hubble distance. Okay. Now let us try to get a specific value for what that is. And to do that, we're going to take a look again at the Hubble law, which is very helpful in this case. So again, this is going to be the the derivative with respect to time of the proper distance being equal to the Hubble law, or like the Hubble parameter evaluated today, which is h naught times that specific distance, which is going to be dp. Okay. And again, we said that this is defined through the fact that this velocity has to be equal to the speed of light. So this means that we can say is that this h naught times dp has to be equals to the velocity of to the speed of light, which is going to be c. And then we can now find what exactly this specific Hubble distance is going to be. And I'm going to put a comma h here so that we are specific about what we mean. So basically we have dp comma h, okay, is going to be defined as h naught divided by c. And since we're evaluating it today, what we find is basically that this distance is at about 4,500 megaparsecs. Okay. So again, once again, because this might be a difficult concept, is just simply a distance that we define through the fact that if we observe a distance, if we observe a galaxy that is moving with a recession speed, so basically it's moving away from us at a speed that is equal to the speed of light, then this is the distance that we define as the Hubble distance, and is given by 4,500 megaparsecs or so. And some of you might be asking yourselves as to how is it possible that an object is moving, or like a galaxy, which is so big, to be moving with the speed of light? Or, I mean, even if you go farther away from this specific distance, are they going to be moving faster than the speed of light? And what we have to think, what we have to remember is that we have a universe, currently we have a universe which is expanding, which basically, what this means is basically, is that if we have two objects in this universe, the expansion of the universe is going to make the two objects recede from each other, so basically separate from each other. And so the objects on themselves are not moving with the speed of light or faster than the speed of light, but the creation of a space is making these objects look as if they are receding away from us with the speeds of the speed of light or faster than the speed of light. Okay, so it's not the objects themselves, it's the space itself which is making them look like they're moving that fast. Okay. All right, and so finally to the last distance that we're going to see today, which is going to be the coordinate or the conformal distance. Okay. And so this conformal distance is basically just the distance traveled by light from a specific time to us today. Okay, is that's how basically we define it. So distance traveled by light from a specific time to a time to today, basically to the time today. And this is what we define that our time today is what we're going to say is T naught. Okay, so T naught. T equals to T naught. And so this distance okay, and which we're going to specify with the chi in this case, is going to be to the speed of light, okay? So basically we're going back to our international system units. We're not in natural units anymore. And then this is going to be the integral from t all the way to t naught. And then the integrand is going to be dt prime divided by the scalar factor as a function of time, prime. Okay, so again, a very simple definition is this is just simply what the distance that light is going to travel given the expansion of the universe, right? Since it's encoded into this scalar factor from a specific time all the way to us today. Likewise, we can define a conformal time. Okay, I'm just going to give you this since it's also important, which is defined with this eta. And then this is going to be actually defined as the integral from 0 all the way to a specific time. And basically what this tells us is basically going to be the time that it takes light to go from the beginning of the universe all the way to some other time. All right, so with this, we've finished the video for today. I hope you learned a little bit. Please let me know if there's anything that is not clear. I will try to help you out. And I will wish for you to see, I wish to see your comments over there and see what else should we talk about. So please let me know. Thank you for watching the video and see you next time.